In this recording, we're going to look at proving the proposition that if G is a group and H is a subgroup of G and A and B are elements of G, that their left cosets are equal if and only if the right cosets for their inverses are equal. And what we're going to do is we're going to get some stuff set up. So first of all, let's think about how we might go about proving this. Well, the first thing is I want to make a particular note. I want to note that what we have is that AH is equal to BH means that the set of A times H, where H runs through all of the H's, is equal to the set of BH, where the little h's run through all of the h's. Now, what this really means is the following. If we have an element C that lives inside AH, that says that C has to be equal to A times H something, and I'm going to call that something for H1. So we have C is equal to A times H1 for H1 inside H. But this also implies, since AH and BH are the same thing, we're also going to know that C is going to be equal to B times H2 for some H2 inside of H. And I really want to basically say this is what my hypothesis tells us. Now, what I want to do is I kind of want to think about how to use that in a way to let me get the thing that I'm trying to show. So what I want to also make a note of is that we need to show that HA inverse is equal to HB inverse as sets. And we're going to do a double inclusion proof. And so the first thing that we're going to do is we're going to show that, so we first show that HA inverse is a subset of HB inverse. So in order to do this, I need to pick an arbitrary element that I'm going to call D, and D is going to live in H times A inverse. Well, what that says is that D is equal to something, and I guess at this point I'm up to H3. So there is an H3. D is equal to H3 times A inverse. Now what I'm going to do is I'm now going to look at D inverse. Now D inverse is going to be H3 A inverses inverse. And we know how to find inverses in groups. We have to change the order of the two elements, and then we hang an inverse on both of them. But of course, A inverse inverse is just A, and so we have A times H3 inverse. And this belongs to AH because H3 inverse belongs to H, which is a subgroup of G. And so it has all of the inverses of all of the elements of H. Well, that means that we now have D inverse lives inside of AH, which is also equal to BH. Hence, we know that D inverse can be written as B times some element of H, and this is going to have to be H4. Well, that is going to tell me that D itself, which is D inverses inverse, is going to be the inverse of b times h4. But the inverse of b times h4 is h4 inverse times b inverse. And what that tells me is that d belongs to h. Got to get that written clearly. This statement over here, that d is equal to h4 inverse times b inverse, says that d belongs to capital H times b inverse. And so what that says is that d belonging to h a inverse does imply that d belongs to h b inverse. And so we have h a inverse is a subset of h b inverse. Now, what I'd like you to do at this point is stop the recording, and I would like you to prove the other direction of inclusion. In other words, what I now want you to do is I want you to prove that HB inverse is a subset of HA inverse by modifying the proof that I just did. So stop the video and do that. Well, hopefully you have tried to actually prove this. It turns out that the proof can be found by making appropriate modifications to the previous proof. And so this is what my proof would look like. The yellow letters are the only things that have changed. In other words, we prove that the left coset BH is a subset of the left coset AH by essentially swapping the roles of A and B for each other. So we wind up having the same kind of hypothesis stuff. We wind up getting the same kind of setup for the double inclusion proof. This time, though, it is the second part. And so we're going to be assuming that D belongs to HB inverse, and we need to show that D belongs to HA inverse. So our D starts off that way, and it's exactly the same argument if you take the time to stop the video and read it. And we wind up showing that D inverse lives in B times H, which is equal to A times H. And hence we have D inverse is equal to A times something in H. And when we look at D as D inverse is inverse, we find out that D inverse, that D itself lands in H times A inverse. And so it's exactly the same proof. And when proofs are this close to being equal to each other, authors of math books will usually state the similarity of the proof with the language of the other inclusion can be proved in a similar fashion. Once we have both inclusions written, it's useful to write a final conclusion that says, since we know the right coset A times A inverse is a subset of the right coset H times B inverse, and we know that the right coset H B inverse is a subset of the right coset A H inverse, we can conclude by a double inclusion proof that we've just completed that the two right cosets are equal. I am going to leave it for homework for you to modify this proof to show that if the two right cosets are equal, then cosets are equal. And that really is done in very much the same way.